Welcome online lecture series in wireless mobile communication. Today our topic is DCS extension of HATA model. Now before we are leading towards this course 231, now recap previous models. Previously we have seen the HATA model that known as HAT 90. It is the empirical formulation of your graphical path loss data provided by Kurma, and it is valid in the frequency range 150 megahertz to the 1500 megahertz. HATA presented the urban area propagation loss as a standard formula and supply corrections equations for application to other situations. These standard formulas for medium path loss in urban area is given below. L50 urban, which is having the unit dB, is equal to 69.55 plus 260 26.16 log of FC, the cutoff frequency, that is the FC, minus 13.82 log of H of TE antenna effective height, TE transmitter antenna effective height factor, and minus A of H of RE, and plus 44.99 minus 6.55 log H of TE and bracket close log of T. This is the main equation of your HATA model. So where this quantity FC is nothing but it is the frequency which is calculated in megahertz, and that frequency range is 150 megahertz to the 1500 megahertz. H of T is the effective transmitter, you can say base station antenna height in meters, which also ranging from 30 meter to 200 meter, and H of RE, which is the effective receiver, that is the mobile station antenna height in meters, and it's ranging from 1 meter to the 10 meter, and D is the separation distance between the transmitter and receiver, which are calculated in terms of kilometers. A of HRE is the correction factor for the effective mobile antenna height, which is a function of the size of the coverage area. Due to this value, H of RE is not fixed in every mobile, so we need some correction factor to calculate for the effective mobile antenna height, which is unique for all the same set of operating radio terminals. So for a small to medium sized city, mobile antenna correction is given by AH of RE is 1.1 log of FC minus 0.7, and it is multiplied by H of RE, and minus 1.56 log FC minus 0.8 dB. For a large city, it is given by AH of RE is equal to 8.29 log of 1.54 H of RE का whole square minus 1.1 dB for FC is less than and equal to 300 megahertz. And same in the large city, this correction factor AH of RE is equal to taken when the cutoff frequency is more than 300 megahertz. So this value is 3.2 log of 11.75 HRE log of 11.75 multiplied by HRE का whole square minus 4.97 dB. For cutoff frequency, it is always more than the 300 degree. Sorry, 300 megahertz. So when we obtain this required path loss in a suburban area, then the standard HATA model equation is again to be modified, and the 50th percentile of this L50 dB is equal to L50 percentile of the urban minus 2 log of FC divided by 28 का whole square minus 5.4. So you need to calculate the 50 percentile in the urban area, and it is separate from twice of the log FC divided by 28 का whole square. Now when we move in a open rural area, we have seen this modified formula is become now L50 dB is equal to L50 urban minus 4.78 log of FC का whole square minus 18.33 log of FC minus 40.98. Although this HATA model does not have any of the path specific correction which are available in a formal model, the above expressions have significant practical value. The predictions of the HATA model compare very closely with the original Okura model, as long as P is taken, as long as we exceed 1 kilometer. So this model is well suited for large cell mobile system, but not personal communication system PCS. So in the absence of this personal communication system, so we need to have cells on in order to 1 kilometer radius. And now move towards PCS extension to HATA model, which is given by European Cooperative for the Scientific and Technical Research Eurocost, and it having another name that is the COST 231. When the committee is working under this to develop an extended version of HATA model, COST 231 proposed the following formula to extend. HATA model is to for 2 kilohertz, and the proposed model for path loss model is euro 91. So the L path loss L50 in urban is equal to 46.3 plus 33.9 log of FC minus 13.82 log of HTE minus AH. यहाँ से इक्वेशन जो है ये इक्वेशन we have these equations 13.82 log of HTE minus A of H of RE plus 44.9 minus 6.55 log of HTE, and it is hold in one bracket and multiplied by this log of the separation distance D and plus CM. CM is a medium sized city or urban sized city, yeah, metropolitan centers parameters. So this is valid in only medium sized city and the suburban, not in a urban area, or not in a open area. Okay, so when open area or an urban area is concerned, the value of CM is become to 0, and metropolitan area centers are considered as 3 dB. So the cos 231 extension of the HATA model, and it is restricted to the following range of parameters. The frequency range is extended 1500 megahertz to 2000 megahertz, and effective height of the transmitter gain is given by 30 meter to 200 meter, and H of RE is 1 meter to the 10 meter, and separation distance small d is 1 kilometer to 20 kilometer. Now this is the most cheated. This slide is taken from the report. So the most often cited of cost 31 model Euro-funded research project categories in 1986 to April 1978, and also called HATA model. So it is summarized cost 31 HATA model, that also known as CS. So the frequency range in Umura HATA model started 1500 to 2000 megahertz, but it is in campus, it is 800 megahertz frequency, which is used for 2G and 3G cellular systems. So the cost 231 HATA model defined path loss is equal to A plus B log of D plus C. It is the very simple summary of that big equations. So A, B, and C are simply, you can say, the equation or equations, and अडॉप्ट किया गया है सिस्टम को लेके आए हैं, और सिस्टम एनालिसिस के बाद इसको डेवलप किया जाता है. So in that case, there are three constants A, B, and C. These are the factors which are depend on the frequency and the antenna height. A is equal to 46.3 plus 33.9 log of FC minus 13.82 log of HP and AH of M. B is 44.9 minus 6.55 log of HB. AH of M is equal to 1.1 log FC minus 0.7 H of M 1. Minus 1.56 log of FC and bracket close minus 0.8, where FC is calculated in megahertz, D is in kilometers, C having the 0 when the small city and medium sized city is treated urban area and sub area. So this is the complete equation. Now in Mura model, this is the percentile medium at value of your path loss. This is the free space propagation loss. AMU is a medium attenuations relative to the free space. G of H of T is called medium attenuation relative to free space. This is the gain factor of the base station factor. Base station the gain factor. It is the effective height of the your base mobile station, and it is also a gain factor. It is the specific area gain due to type of the environment. Thank you very much.